One. Welcome back, everybody. So this. Is he mocking me?
No, you're off. Really, he's gonna start his vlog. Like and subscribe.
Welcome back, everybody. Don't forget to click the subscribe button below. There's a link for the merch. And I'm like, what would be Mr. Leverett? Like, yeah, like a calculator cover.
Oh, my daughter was sick.
Asterisk. Spot
Yeah, really.
Special guest.
Special guest. All right, here we go. So again, we decided to keep the quiz for tomorrow. Section 4.9 and 5.1 quiz. Heavy on the 4.9, right? You see that from the review. It's mostly 4.9. The stuff from section 5.1 is just going to be a couple area problems, and then we got a velocity problem on the end there as well. What should you not forget about for all of these antiderivatives? The plus C. Honestly, that's probably where I'm going to have to take the majority of the points off. But don't let that be you. Just to remember the plus C at the end. Okay, so the rules for the polynomials. Remember, kick it up and divide by the power, right? Raise the exponent and divide by that new exponent. So in this case, this is going to be 3x squared over 2 minus 4x plus c, right? I don't care if you... What's wrong? Give me a weird look. Did I really? No, I'm good. I don't have a key for this. I'm just going cold turkey here. I don't really say that. Just set myself up for failure. Maybe I'm just lowering the expectations for you. I really don't care if you put it as a 3/2 or 1.5. You put that 3/2 out front, leave it as a fraction like that. Really don't care. Whatever you want to do there. Yeah. Just make sure if you leave it as a fraction, make sure it's a reduced fraction. Find the most general antiderivative of the function f of x equal to 4x to the third plus 5/3 x squared minus 4x. All right. So we got a 4x to the fourth over 4 plus 5/3 x to the third over 3 minus 4x squared over 2 plus c. I know I got to reduce some there, but in general, that's what we got. Right? Raise all the exponents and then divide by the new ones. Okay, so this is going to give me an x to the fourth plus, okay, we got to do a little work here. 5/3, if I want to divide by 3, isn't that multiplied by 1/3? So really, that's 5/9. 5/9 x to the third. You want to put it as decimal, 0.5 repeating? Sure. Minus 2x squared plus c. See, that's why I could never be like an elementary school teacher. Like, how do you teach a kid that like 1 + 1 actually equals 2? Or like, you know, like those basics that it's just like, it's just this. It's just this.
Hey, make sure they start at 0.
Right.
Yeah, make sure they start at 0 when they count.
All right, so there's 1 and 2. There's my answer here for 2. Let's take a look at question 3 and 4. Oh, oops. Whatever. Yeah, it's keep change flip. That's basic. Come on. All right, find the most general antiderivative of that function. Now, it starts to get a little funky with some fractional exponents. So we have 2x to the 3/4 power. So it's that's not 2x to the, okay, we go from 3/4, we go up 1 whole unit. Uh-oh, these fractions are killing. 3/4 plus 1. Right, 7/4. Good. 7/4. 2x to the 7/4 divided by 7/4. Uh-oh. Now, plus, okay, I raised it 1 unit, right? -2/5 plus 1. So -2/5 If I want to do plus 1, that's plus 5/5. So 3/5. So 5x to the 3/5 divided by 3/5. Plus c. Plus the constant. Okay, let's mess with that fraction a little bit. We got 2 divided by 7/4. So keep, change, flip. So that's 8/7. So 8/7 x to the 7/4. And then again, another keep, change, flip, keep, change, flip, which is 25/3. Plus 25/3 x to the 3/5 plus c. Good there? All right. Okay. I love some trigonometry. 4 sine theta minus 3x. Actually, looking at that, that should probably say those are 2 different variables. It really shouldn't be 2 different variables. That's bad form, Mr. Laverick. Bad form. We'll call that theta. I should have really said 4 sine x minus 3x or 4 sine theta minus 3 theta. Those are disagreeing variables. So sorry about that. Bad form. Bad form. Okay. 4 sine theta. So remember, I like to do it this way. What is the derivative of sine? Cosine. What is the derivative of cosine? Negative sine. Right? So let's work it backward. Right? Okay. So now this means if I start with sine, right? If I start with sine, this negative has to transition over to the other side. So what is the antiderivative of sine? What's the antiderivative of sine? Negative cosine. Right? Negative cosine. So negative 4 cosine theta minus, now this 3x, 3 theta, whatever you want to call it here, works exactly like any other polynomial. So we're just going to say minus 3 theta squared over 3. Or sorry, over 2, excuse me. Make sense? I'm not going to go any funkier on the trig other than just sines or cosines. Yeah, right. Again, I'm not going to go any weirder on the trig other than sines or cosines. That's all you'll have to do. So I know on the table there you had tangents and cotangents, all that junk. I'm just going to stay simple, and we're just going to look at sine and cosine. Oh, shoot. Oh, would you do me a favor?
Yeah.
I totally forgot to give this girl her pass. Uh-oh. You bringing me that pass totally reminded me. And now you're going to do me a solid and find this girl for me. Kaylee. Where is Kaylee Copeland? Where is Kaylee Copeland? Second period. Second period. She's in Spanish. Would you take it to Miss Ardilla's room?
What room is it?
That's a great question. 222. Ooh, that's an easy one, I wrote. 222. I'll write it down. Thanks. Okay, which pass did he just give me? It's Vince. Oh, Vince, you gotta go now.
Where do I gotta go?
I don't know.
I gotta go right now.
It says immediately.
I can't wait. Yes. It's for CCP.
I don't know. It says immediately.
No, it's like the.
It's Miss Gardner. It's
Yeah.
Oh, yeah. All right. Any questions before so far? We good? Okay, let's take a look at number 5 now. Here we are. Here's number 5. Okay, so I am given f double prime. I want to find f, right? I'm given f double prime. So I've got to go 2 iterations back in terms of the antiderivative. So let's find f prime of x. Okay, so that's 16x to the 4th over 4 minus 9x cubed over 3 plus 10x squared over 2 plus c. Now, are we given any additional information to find c? No, so it's just got to stay. Let's reduce that a little bit, though. That's going to turn into 4x to the 4th minus 3x cubed plus 5x squared plus c. There's f prime. So now, working it back to f, that's 4x to the 5th over 5 minus 3x to the 4th over 4 plus 5x to the 3rd over 3 plus, now that c has to add an x with it, cx. And now I add on a new constant. We'll call that d. You can really call it whatever letter you want. Just it's unknown. Yeah, that's it. There were nothing to reduce in terms of the fractions. Good there? Again, the c and the d, you can write any letters you want. We just normally write c and d. Okay, let's take a look at the next one here. Number 6. Okay, so now I am given acceleration, and I am asked to find position. Remember, position is the antiderivative of velocity, and velocity is the antiderivative of acceleration. Remember, they chain together like that. So velocity, v of t, is 7t squared plus 2t, 7t squared over 2 plus 2t plus c. But the nice thing here is, what is my constant there at the end? 6, right? Again, I didn't need to give you my v of 0, right? I could have given you any coordinate. I could have told you the velocity at 1 or velocity at 10. If that's the case, you just plug in that as your x value. So in this case, it was just a 0. Plug in 0 as your, so t value in this case. So plug in 0 as your t value and that as your v of t, so 6. So we would say 6 is equal to 7 times 0 squared plus 2 times 0 plus c, but those go away. So I can say that v of t is 7 over 2t squared plus 2t plus 6. If you wanted to make that a 3.5, that's fine as well. And now position is the antiderivative of velocity. So position, s of t, is equivalent to 7 halves t to the 3rd over 3 plus 2t squared over 2 plus 6t plus d, whatever, letter. It's going to be replaced in a second. And now we just simplify. So s of t is equal to, 7 over 2 times 1/3, so 7/6. 7/6t cubed plus t squared plus 6t plus, and now again, I am told my 0. That's the best case scenario when you're told your initial, right? Initial displacement was 2, positive 2. Good. So I know that my d value, my constant at the end, is 2. So now, based on that acceleration and knowing initial velocity and initial displacement, I can say that x position is defined at any time t here. All right. Good here? What's wrong? We good?
Well, I'm just looking at it.
Just soaking it in? Okay, here. There's the full picture. We good? You got photographic memory, you just take a picture.
I mean, it's S. Is it just like the position? Like if we
Yeah.
started with the position that took like the double derivative?
Yes, yeah, just working it backward. Double antiderivative. Next one up here. Okay, now this is where it starts to get a little weird. Right? Here's the things that you need to pay attention to. You need to pay attention to whether I'm doing right side, left side, or midpoint. I could ask you any one of them, right? You have to know how to do right side, left side, or midpoint. Look at the function, know what the graph is generally going to look like, and then know your endpoints. Okay. So it says estimate the area under the graph of f of x is equal to the square root of x from 1 to 3. Let's start by just graphing that. I will ask you to sketch a picture. Right? I will ask you to sketch a graph of the approximation. Okay. So here, I know I got 1 to 3. Right, so here's 1, here's 2, here's 3. Space it out a little bit. And then look at your function. Okay, the square root of x. If I plug in 0, I get 0. I know that's outside of what I'm looking at, but still. If I plug in 1, I get 1. Let's put 1 here. If I plug in 2, I get radical 2, which is like 1.4. 3, radical 3. Let's stretch it all the way out to 4, because that's going to be 2. 4, 2. So here is my, yikes. Curve it up. There we go. I know it's going to keep going past that, but I really don't care about that. I really only care about this piece in here. Right? The area under the curve for that, in that section. Okay, so let's do R4. You know what I'm going to do actually, because I'm going to have to do right endpoints then left endpoints. Get out of here. I'm going to do this. No. Okay, good. Just so I don't have to draw that all again. All right. So let's do R4. Now, remember, R4, there's really 2 ways to set this up. I think in the key for this, I had put delta x all the way in front, right? In the key for the homeworks. I was putting delta x all the way in front. You can either put delta x with every y value, because that's the width of each strip, right? You can either put delta x in with each y value or factor it all the way out. Sometimes it's easier just to write it as factored all the way out. Well, what is delta x in this case? Well, delta x is always b minus a over n. So b is 3, a is 1, n, we're doing R4. So 2/4 is 1/2. So delta x is 1/2 in this case. That's going to stick both right side and left side.
I don't understand why we're doing R4.
Didn't I say... Oh, 4 approximating rectangles.
Okay, so, but are we approximating from x equals 1 to 4?
No, we're approximating from 1 to 3 using 4 rectangles. What are you talking about? What are you talking about? Yeah, right there. We good now?
Yeah.
Thanks. She tried to say that in the most polite way. I don't understand why you drew that line. All right, so we got our delta x 1/2. I'm going to put that all the way out in front, right? I just factored it all the way out. Okay, so now I'm just going to line up my 4 y values. Now this may change depending on right side versus left side approximation. I would have called it. Okay, so now look at my full length. It's 2 units, right? Okay, I'm gonna each rectangle's width is 1/2. So that means I've got to go make a little partition here and here. So this is 1, this is 2, this is 3. So this is going to be 1.5 and 2.5. at each one of those locations, I have a value on the right side. So here is my right side approximation. Right side of my rectangle. 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 You follow me there? That's right side approximation. Okay, now think about this. Am I going to be using f of 1 as a location that I'm trying to find? No, I don't actually use that coordinate right there, right? Also, I could think about it this way. Wasn't xi a plus 1 or a plus I delta x, right? So if x1 is 1 plus 1 delta x, so it's 1.5. That's x1. That's right side approximation. So this is 1.5. That's the first one that I start with. Now it's f of 1.5, so it's radical 1.5. Then I do the y value. Next subsequent y value is 2. Radical 2. Then 2.5. Then 3. Again, you could have distributed in that 1/2. 1/2 times radical 1.5. 1/2 times radical 2. 1/2 times, but again, I just like to factor that out. Let's see what we get. 0.5 times, we have radical 1.5 plus radical 2 plus radical 2.5 plus radical 3. Right. 1/2 times each of those 4 right side y values. 2.98. 2.98. So R4 is approximated to be 2.98. Good so far? Okay, so let's take a look at, and is that an over approximation or under approximation? That one's an over, right? Because I see extra area added in there. Okay, let's take a look at this one. Let me fix this one. Scroll down a little bit. There we go. Okay, so this one is going to be left side approximation. Right? I still have these, intermediate points here. This is 1, this is 3, this is 2, this is going to be 1.5, and this is going to be 2.5. But now I've got to go left sides. So this is going to be the left side here. It's going to be the left side here. It's going to be left side here. And the left side here. I mean, you can really take the square root of an angle. There's stuff there. I say the exact same thing my freshman. If I said there's things that you don't know, they'd be like, who? Okay, so L4 is going to be same delta x, same 1/2, times all of these y values. I've got 1, 1.5, 2, 2.5. Do I use f of 3? No. Which is very similar to how we're going to calculate the velocity ones. One uses the first point but not the last. One uses the last point but not the first. All right, let's see what we got here. Now I'm just going to go back in and run this same number, but instead of 1.5 or instead of 3, I'm going to say I need f of 1. Okay. So we got 1, 1.5, 2, and 2.5, which is going to be 2.61. L4 is 2.61. Is that an under approximation or an over approximation? Under. So does that make sense that one is smaller than the other? Yeah. So I know the true area of this thing is somewhere in between 2.61 and 2.98. Somewhere in there. If I were to run more rectangles, that would get me a little bit more precise. Questions about that? Do we all know how we would do midpoint? You want to do a midpoint? It could be. Could be. Let's do that real quick then, if we're confused about it. Here, let me get this. Let me get this. Let me clone. Let's just go to a new page. Let me move you over here. Okay. Ungroup. Okay, let me get this out of there. Let me get this out of there. This out of here. All right. So if I wanted to do midpoints, I know these are still the lengths. Like I know this first rectangle is still from 1 to 1.5. What is the midpoint from 1 to 1.5? 1.2. Right? So I know I'm going to use 1.25. What's the next x value I'm going to use? Well, just add a half, remember? Aren't these strips a half unit in length? Okay. So this is 1.75. This is 2.25. This is 2.75. Okay, so now just eyeball it up. Here is where that 2.75 runs. Here and here. This is where the 2.25 hits. Here and here. This is where the 1.75 hits. Here and here. And this is where the 1.25 hits. There and there. So you would just be taking 1/2 times, radical 1.25 plus radical 1.75, 2.25, 2.75. That's midpoint approximation. The tricky part is just figuring out where the midpoint was, right? Figuring out what that 1.25 actually was. And then just keep adding 1.5. Add on your half unit in length that you've got. Just using those x values to plug it into the y values. Make sense on that now? We needed to do that. Okay, let's take a look at the velocity problem that we had at the end. Distance. I guess it is kind of velocity. All right. The speed of a runner increased steadily during the first 3 seconds of a race. The speed at a half-second intervals is given in the table. Find the lower and upper estimates for the distance that you traveled during the first 3 seconds. So notice here again that I am increasing in speed, right? I am taking half-second intervals and I am increasing in speed. The speed is increasing as I start to run over the first 3 seconds. So what we're going to do is we're going to take this half-second interval, apply it to here, apply it to here, 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 and here. Then I'm going to do the other approximation, right? Then I'm going to go to here, to here, to here, to here, here, and here, right? That's going to give you the lower boundary and the upper boundary. Again, don't forget, the exact same way we calculated the areas, left side, just jump back to this slide here real quick. The right side approximation used the last point, but not the first. It didn't use 1, but it used 3. The left side used the first, but not the last. Used 1, but not 3. It's the same thing is really going to be true with this. This under approximation is going to use 0. The red is going to use 0, but not 15.3. The blue is not going to use 0, but it's going to use 15.3. So that's where I get my 2 different answers here. So let's do the red. right? So again, I'm going to factor out my delta x. My delta x, again, in this case, is a 0.5, is a 1/2. But I'm going to factor that out. I could say 0.5 times, 0.5 times, 0.5 times. Why? So I'm going to say all my reds are, the y value is 0, 6.7, 9.9, 12.2, 13.6, and 14.7. Again, there's nothing to plug it into there because that's the actual y values. You got actual data, actual x and y. And again, we could factor that in, but I'm just gonna put it here. 0.5 times, okay, it was 0 plus 6.7, 9.9, 12.2, 13.6, 14.7, and I don't use 15.3. Oh, that's a 147. Let me just double check, spot check my keys in. Okay, good. So this is the under, 28.55. And that is feet over the first 3 seconds. Okay, let's do the blue approximation. That's 1/2 times, oh no, not the 0, excuse me. 6.7, 9.9, 12.2, 13.6, 14.7, and now the 15.3 is added in. I'm basically saying from this 1/2 second interval, we're going to apply 2 different speeds to that 1/2 second interval. The first one being the 0, the under being the 0, the over being the 6.7. And then chaining that all together. Okay, so we got 0.5 times, I'm just going to re-enter this. 0.5 times, and then I just want to add on the 15.3. All right, 6.7, 9.9, 12.2, 13.6, 14.7, and 15.3. So 36.2. So I know my true distance traveled over the first 3 seconds is somewhere in between 28.5 and 36.2 feet. And this is all based on, me observing the velocity every 1/2 second interval. Just seeing what the velocity is. Questions about that? Yes.
How would you find the midpoint?
I wouldn't ask you to do that, but honestly, it wouldn't be too bad. But I'm not giving. You would just be taking the midpoint of this. So, like, you'd be taking 0.25. Well, there's no way to find the y value. Yeah. See, like for the other one, I could figure out what the y value is in between here, in the midpoint of this. But because there's no equation, I can't do that. Yeah. Okay. We good there? Cool. Let me stop the video.